My name is Maximilian Bierl, and I'm product manager for large bore engines and single cylinder engines at FEV. My professional past is also in the industry of a manufacturer for medium speed and high speed engines and also slow speed engines here in Germany. So I will today say something about our single cylinder engines. And now here in the first slide, you can see our complete program of all single cylinder engines we are offering to our customers. So you can see we have a full scale starting with the S10 on passenger car size for bore sizes from 65 to around about 110. Step over to a truck size for truck size cylinder tailor-made single cylinder engine S14. Then the next bigger size is the S20, covering the high-speed engines, bore size from 140 to 200 roundabout. The next model we have introduced to our single cylinder engine family is the S30, which covers the smaller medium speed engines and also a big portion of the high speed engines. So is some combining tool for power units coming from these both markets. Then we have the S36, what is a classical medium speed single cylinder engine for bores up to 365 millimeter, covering a wide range of medium speed engines. And then the two big ones, which are going up to 600 millimeters, S40 and S55, where we can integrate really the biggest four-stroke power units which are available in this world. So why are so many companies more and more using single cylinder engines? What are the main drivers for that? So here you can briefly see save time and money. Of course, when you run prototype testing hardware, which are usually very expensive parts because they are produced not in serial lot sizes, they are produced most likely on special setups of machines and so on. So testing prototype parts are relatively expensive, usually special pistons, special injectors, and so on. And this is the first benefit, that you need them just one time for a single cylinder engine and not 6 times or 12 times. So this is the first big benefit which a single cylinder engine is offering. The other thing is, of course, the fuel consumption. The bigger the cylinder is, the fuel consumption is a significant cost factor. And when you run, for example, a 12-cylinder engine with 1,200 kilowatts per cylinder for some hours, you can really see this also on your financial account that there happened something. Of course, also to go into overloads, to go to new load levels like higher peak firing pressures and so on, is much more easier with the very oversized and robust single cylinder engine as with a serial engine, which has the value of some several hundred thousands of euro or even millions, and where you are more careful with going into overloads and things like that. So here we can see briefly again, more in detail with all these technical values, which bore sizes, strokes, displacements, speeds, and so on are covered by these different type of engines. So I do not want to go in detail now. You also will get the handout and will also have these informations available for you to read it. But just to mention, as you can see, we are, for example, from the speeds, always on a top level, much higher than what is usual, typical for that market where the single-cylinder engine is made for. And as you can see, the maximum speed on our smallest one reaches up to 10,000. And this is also just a nominal value. We even have some of them going on higher values, and even companies doing Formula One engines are using our single-cylinder engines for testing and to develop their engines. So again, here we can see the cost-saving potential when you operate a single-cylinder engine compared to a multi-cylinder engine, full-size engine. Of course, the bigger the cylinder or the engine is, the bigger also this cost-saving potential is. And of course, it is also a question of the scenario you are comparing it. How many variants do you test and run per year? So there is some spread, of course, of the cost saving which can be identified, but it is at least in a range that when you do a total cost of ownership calculation, the single-cylinder engine is more or less paying itself by this savings which it is offering. So as we can see here now, how is a single-cylinder engine implemented into the development process? So when you have a single development process without a single-cylinder engine, you get relatively late real feedback from your engine, from the combustion measurements and so on, and also from the mechanical functions, if really everything works like it is calculated or simulated. And when you integrate, this is shown here in the upper path. And when you look into the lower path, where we also have integrated the function of a single-cylinder engine, you are much earlier in a typical development process of an engine, be able to test these parts, to do first mechanical testings, so to also do thermodynamical testings, and to get a first feedback of all these things working together and how much earlier. And then we know development projects where you really can introduce already these results to the first full-size multi-cylinder engine prototypes, which get built up. And so you have already a first loop done and integrated in the first multi-cylinder engine. So here we can see which common features our single-cylinder engines have. So all of our single-cylinder engines have a first and second order mass balancing system. So the vibration level is very, very low, and so there are no issues with vibrations which gets into fundaments and buildings and can disturb, for example, production processes or something like that. So then, of course, the gear drive is arranged in a way that all possibilities of timing drives can implemented into this modular system. We have full flexibility for adapting different valve train systems. All these different types of to drive valves like DOHC, OHC, UHC, Miller, Atkinson, and so on are already in reality applied and realized on our engines. Of course, a single-cylinder engine is very flexible on fuels. you in the end can run every kind of fuel. We also have already applications running on hydrogen, where we also developed the safety concept for this kind of operation. And of course, all these fuels which are known to us from the past and also which can be seen for the future. What is also a standard thing is that the cooling system, lubrication system, and charger system is put to external conditioning units, so that the single cylinder is really an independent tool, and all this other stuff can applied by these subsystems in a way like the customer needs it. Here also is shown the general setup of our single cylinder engines. As you can see, the more it goes up, it becomes customer specific, or the more it goes to the lower regions, it is standardized. So typically the power unit is something what is supplied by the customer, and the single cylinder engine gets adapted to this power unit, and all this gets attached and integrated into the base engine, which is developed and produced by FEV before this happens. So the crank balancer unit, which is carrying the balancing system, and the crankshaft is starting from the bottom. The first thing, standardized, more or less always the same parts. Then the crankshaft, which gets adapted, of course, to the stroke and to the connecting rod from the customer. And then the liner housing, which is a part individually made for a certain power unit from the customer. And then in this, the power unit gets inserted. We will see this more in detail also on the next slides. So all of our single cylinder engines are made of one-piece casting parts. So we have no welded or steel welded or something like this parts on this high-loaded and very expensive central parts. So and also all this what can get of problems of welded single cylinder engines, which are known, generally cannot happen here. Combustion forces from the crankshaft are directly guided into the CBU. We will see this also later, because the crankshaft is assembled from the top, and the forces go directly into this big part. The balancer shafts can be mounted from the top. The crankcase is independent from base frame. So the base frame structure can be adapted to the demands from the test cell boundary conditions. So here on the top, you can also see our standardized gear train system from crankshaft to balancing system. What I already mentioned, the compensation of first and second order mass forces. That we use hydrodynamic bearings for the idler gears, and can also adapt different small differences in the mass forces with separate weights on these balancing shafts. So here is the assembly process, shown how a general setup of our engines is going on. As you can see, we already saw the base unit assembled with the balancing shafts, and then the crankshaft gets inserted. The main bearing covers get attached. Both happens from the top, what makes an exchange later much easier if this is in some other way done. You can see here as an example how this looks like, then also with how real parts are looking. You see that very massive crankshaft, and Also, this part is always made for 300 bars. Of course, the power unit which we are using has to be able to stay the same peak firing pressure. In some cases, we develop power units on our own. I will mention this later, where for universities, for example, where then the customer has a completely 300 bar or even higher capable power unit, and of course single cylinder engine. Then we attach from the top this liner housing, which is the interface to this, in most cases, individual power unit coming from the customer. And as you can see, is now attached here to that engine. And then, flywheel adapter and so on gets also assembled to that engine. And then finally, the power unit gets installed, what is usually, like I said, coming from the customer, but in some cases also can be developed completely from FEV. We have cases for that when some institutes or so do not want to use special dedicated OEM power unit. So then we see the accessories around the single cylinder engines, electrical driven fuel pump, common rail system, turning device, and drive shaft through to the dyno. And then flywheel cover and blow-by breather and engine feet get attached. And and then we have we close this engine with the covers, attach the crank speed sensor, explosion valves, and engine oil inlet filter briefly before the engine is then fully assembled. Last thing is these vessels we use for the intake and for the exhaust system to damp the gas dynamic vibrations in the system so that the gas dynamic behavior can be adjusted to a comparable level of multi-cylinder engines. And and then we see the engine frame. What I also want to mention, but unfortunately cannot go so much in deep detail now because of the time reasons, is that for all our single cylinder engines, also optical investigation units are available or already applied. And as you can see, it is the base setup is the same engine, and it's only a special on top system which gets attached and offers from all sides an optical access to the combustion chamber, and also, like you could see on the introduction picture, for the access of laser beams to stimulate the emission of radiation of the combustion gas. Here is an example from an S20, a high-speed single-cylinder engine, how this looks like in reality in our workshop. And so you see it's a more or less fully machined high-quality part for mechanical engineering. So to sum up, with our single-cylinder engines, we can offer high flexible tools which helps and support the complete development process. One of the main focus is, of course, the combustion research on the test bench, but also other research is already done, mechanical investigations. All these engines are offering a high potential for the future research. So alternative fuels, different combustion systems, and also very high peak firing pressures can be tested. The setup of this engine is standardized and also modular with variable design. So it is very easy to adapt these setups of the single cylinder engines to the special requirements from each customer. Like I mentioned, optical access is also an option, as also fully variable valve trains, what we also have already in operation, working on electronic hydraulic systems, where you can you're fully free how often a valve opens, when it shall open, and when it shall close, can be without any limit to a mechanical system adjusted. And yeah, there's also our single cylinder engines are offering several options for investigation, measuring, and tracking. And the whole family covers all size of four-stroke engines somebody can imagine. So with this, I close my speech and say thank you very much for that attention.